Okay, so today we're starting a new unit of the course that has to do actually more with an area of computer science called computational complexity, which is the study of classes of problems as opposed to specific problems. A powerful tool within the area of computational complexity is the notion of reductions, and that is something that is going to be a theme through, I guess, the next 4 lectures, today and the next few lectures. And today I want to, at high level, motivate this notion of reductions. And we'll do that first with an example. So we'll start, like always, put down some computational problem. Today is going to be bipartite matching. We'll solve it. And then we'll kind of look back and try to kind of abstract away how we solved it and what we can learn from it. And then we'll have some general formalism of how problems can relate to one another. That will kind of lead to the notion of a reduction. Well, that's kind of the plan for today. So as I said, let's first start with a motivating example. And we're going to study the problem of bipartite matching. It's a combinatorial problem defined on graphs. So specifically, we're given as input a bipartite graph. So what is a bipartite graph? It's a graph with 2 parts. So specifically has left vertices, right vertices, and an edge set. Okay, and the edge set is only between left and right. So kind of the picture you should have in mind is that you have some number of left vertices and some number of right vertices, and there are edges only between left and right, but not within left or within right. And we want to find a matching. So matching M. So what is a matching is a set of edges in this graph where no pair of edges touch the same vertex. So we'll see an example in a moment. And the goal is we want to maximize the size of the matching, the number of edges in the matching. Okay? So also I should say this is called the maximum matching. The absolute largest matching. This is distinct from the a maximal matching, which is when you have a matching that cannot be extended further. So where does this problem come up? When, maybe for example, you have some tasks and you have some processors. The tasks are your left vertices and the processors are the right vertices, and you want to kind of assign jobs kind of all at once for concurrent processing. So you're just basically assigning resources in a way that is mutually exclusive, right? No task can be assigned to multiple processors. There's no point. When processor is assigned, it's just working on it. And when the processor is computing, it's computing only on one task, okay? Or maybe you're trying to match up people in some way. So, maybe in the example up there, you want to find a matching. By the way, a matching without making it big is very easy. That's the empty set is obviously a matching. I could just put in, say, this edge. That would also be a matching. But if I also add, say, these 2 edges, then now it becomes a maximum matching because I have a matching of size 3. There are 3 vertices on the left, and certainly I will not be able to increase this matching further. Now, of course, on small, cute examples, we can eyeball it, but the question is, how are we going to solve bipartite matching in general? So today we'll see, and if we really deeply cared about bipartite matching, we can have a longer discussion about what are reasonable approaches to solve this problem. And we can go back in our toolkit and say divide and conquer, greedy, DP, and one of these may point us in the right direction. Today, I don't want to spend too much time sort of thinking about how one may solve this problem. I'm just going to talk about a particular way of solving this problem that relies on solving another problem that looks nothing like it. Specifically, it's going to be max flow. So we're going to be using the max flow problem to solve bipartite matching, and we'll talk about that. And then we'll see some of the features of this solution and how it kind of it starts pointing in the direction of reductions. So now I want to talk about to solve bipartite matching via max flow. Okay? So if you remember, so we've seen max flow. We had 2 lectures on it before spring break. Max flow is also about graphs, but it's not quite bipartite graphs, right? So if you think about, if we're going to be using a max flow subroutine to help us here, the max flow subroutine really understands different things. It expects, for instance, a network. Networks are directed. This is an undirected graph. Also, networks have capacities. Where are the capacities here, right? This is an undirected sort of graph. It has these 2 parts. So yet somehow we're going to be able to kind of take our instance of the bipartite matching problem and turn it into some network, and somehow finding the maximum flow there will help us understand the maximum matching. So I'll write down what we're going to do, and so we're going to talk about it. So let's say that you have I'm going to write it a little bit bigger here. Say that you have your bipartite matching instance, your bipartite graph, right? So here it is. So that's left and right. So what we're going to do is we're going to take this instance and turn it into a network. So we're going to introduce an additional source vertex S off to the side. This is neither left nor right. It's just, I guess, left, further out. And we're going to connect it with directed edges to all of the left vertices. We're going to introduce a sync vertex T, and we're going to connect it with directed edges from all vertices in R. And then we're going to orient all of the currently undirected edges that were already part of our instance. So here I'm adding arrows to all of the edges that were already present. So now we have a directed graph, but in order for us to talk about max flows, we also need capacities. So intuitively, kind of what we're trying to do is we're going to try to set it up in such a way that pushing a lot of flow from S to T is going to be tantamount to finding a matching on the original instance. So the idea is to say, well, look, let's just put capacities 1 on each of these. These are on each of the edges from S to L and from R to T. And we're going to put capacities 1 also on all of the now oriented edges from L to R. The intuition being here is that if a flow pushes a unit of flow onto an edge, then somehow this unit has to go somewhere. Now, hopefully it will not get split, but if it doesn't get split across these different edges, then we can interpret that unit of flow as a choice, as saying, please take this edge and put it into the matching. Okay? And intuitively, if we're able to push many units of flow from S to T, then that would select more edges in here, right? And if you think about the fact that we're pushing 1 unit of flow here, and we are only allowed to take out 1 unit of flow, intuitively, this, and we'll prove it in a moment, this prevents the flow from picking multiple edges, because if, for example, this vertex over here receives 2 units of flow, but only pushes out 1 unit of flow, that's not a valid flow, because it would violate conservation of flow. So this is kind of the intuition. But there is this worry that kind of, what if flows get split, right? So for instance, suppose your graph looked like this. So let's look at whether this would be bad for us. Let's say that I had a simple tiny instance. And let's say that I pass a unit of flow on each of these and 0.5 on all of these internal edges. So this would be a max flow on this instance, and it looks like a worrisome example, because this inner part of the graph could have been our beginning bipartite matching instance, right? Our bipartite graph. Yet, yes, this is a max flow, but there is another max flow on this very same graph. The one, for example, that pushes 1 unit of flow, let's say, on the 2 parallel edges there. So, how do we make sure that that we don't end up here, but we end up here? And is this something that always is possible? Well, we should remember that when we were discussing maximum flows, there was a fact that I'm sure was mentioned in lecture that if we have integral capacities on the network, then there exists an integral flow. And this was basically kind of clear from the max flow algorithm that we saw, the Ford-Fulkerson algorithm, for instance, because the way that we were finding the maximum flow was to consider the residual network, find a path in the residual network, and take that path and add it to the flow. And each of these paths in the residual network would consist of integral units of flow. So you start with an empty flow, you add a path from the residual network, another path from the residual network. Each time you keep adding integral paths, or rather, paths with integral flows, and at the end you end up with a max flow with that is integral. So this fact tells us that on this network there is an integral flow, okay? And so now I want to sort of informally argue that there is a correspondence between matchings on the bipartite graph and integral flows on the network derived from the bipartite graph. This is going to be a pretty simple argument, and then we'll kind of sort of finish this this simple motivating example. So, I'm going to say claim, or rather, let me just write first the correspondence. We're going to now argue that I'm going to write it up here. We're going to argue that there is a correspondence between matchings on the bipartite graph so I'll call them matchings M on the bipartite graph, and they're going to be a correspondence with integral flows F on the network. Let's call it G tilde. This is starting the bipartite graph and modifying it in this way. And this correspondence is such that if a matching has a certain value, has a certain size, then the corresponding flow will have its value being the size of the matching. Okay? So we're going to now prove this correspondence. There's two sides to it. The first claim says, suppose that M is a matching on G, then we want to show that there exists an integral flow F on G tilde such that the value of F is the cardinality of the matching. So this proof is pretty simple, right? Because look, this is the network that we're on, and we have some matching. Say we picked, say the matching says, but it doesn't have to be a maximum matching, it's just some matching. So say that the matching says, please pick this edge and this edge over here, right? So now we sort of go in the network view, and we say, okay, we need to find a flow on the network, integral flow, whose value is the size of the matching. Well, that's pretty easy. We just look at which edges on the left are selected, which edges on the right are selected, and we push one unity flow to all the selected edges, travel along the edges in the matching, and then we pull out one unity flow from all of the selected edges from R. And because M is a matching, at no point there are any collisions anywhere. We respect the conservation of flow. So the proof is that you push one unit of flow from S to kind of a L, let's call it L of M. So these are the left endpoints of the matchings. And then across M, and then from R of M to T. And since we're passing one unit of flow, so the value of F is going to be one unit of flow for each edge so per edge, and then we have M edges. Okay, and so that that proves this claim. Okay, so all right, so give me anytime you have a matching, I can extend, I can turn it into an integral flow on the network G tilde. This is not surprising because it was kind of the intuition behind this construction. So for the other direction, say that we have F is an integral flow on G tilde. I want to say that there exists a matching M on the regional bipartite graph G such that the size of M is the value of F. Now, because F is integral, then any edge in M either carries 0 units or 1 unit, because the capacities are 1, so it either carries 0 units or 1 unit. So now we're going to say set M to be the edges carrying 1 unit. All right, so this is, now M is a set of edges, but we need to argue that it is a matching. For it to be matching, we need to make sure there are no edge collisions on the left or on the right. But look, say that we have some edge on the left. And there are sort of edges coming out. we know that because we selected this, and we have selected at least one edge that touches this vertex. Say by way of contradiction that there are actually two. There are now two edges in M that were selected. Because we selected them, it means that both of them carry one unit of flow. But going into the vertex L from S, there is only capacity 1, right? So a picture like this would violate conservation of flow. So it cannot be. And my symmetry on the other end, if by way of contradiction, somewhere on the right, in the matching M, we selected two edges that point to the same vertex, we selected them because they were carrying one unit of flow. But out of that vertex, there is only one unit of flow that is allowed. So again, this cannot be because of conservation of flow. And because of this, we know that M is a matching. Okay, now what does it tell us is that there is a correspondence between matchings on the bipartite graph and integral flows on the network G tilde derived from the bipartite graph. And this correspondence preserves size in the sense that the matching size will correspond to its flow's value. And this brings us back to this original question of solving bipartite matching via maximum flow. What we can do is to say, given a bipartite graph, construct this network, run the max flow algorithm. Maximizing the value of the flow is tantamount to maximizing the matching, so that once I find the flow that is maximal, I can just read off from it the matching, which is basically the edges that were selected and carry one unit of flow. A small technical note is that in Ford-Fulkerson, the algorithm we saw in class, the time is a number of edges times the value of the maximum value of the flow. And we remarked that this is not quite polynomial time. It is weakly polynomial time because the value of the flow, maximum flow, could actually be exponential in the input size. But in this case, the number of edges in the network is whatever we had before, which was E, right? Size of E, let's call it M, plus we added edges here and added edges here, okay? So it's like L plus R, right? So in our case, number of edges is E plus L plus R, which you can think about it as like order of M plus N, where M is the number of edges in the bipartite graph and N is the number of total vertices. And the max value of the flow is certainly no more than this cut, and this cut would be N. So that the running time to solve bipartite matching is M times N. Actually is strictly polynomial time in this particular case. Okay, so now we solve bipartite matching. For us, bipartite matching today only plays as a motivating example. So what was motivating about it? So some features of the way we solve this problem today are the following. So we got an instance, a bipartite graph, and somehow we kind of embedded solving the problem into something that a priori looks very different, just like networks. These are directed graphs, they have capacities. And so this was what we're going to call a pre-processing. Okay, so we pre-process the instance from an instance of bipartite matching to an instance of max flow. Then we said, okay, we just run some max flow subroutine. In this case, we happen to have Ford-Fulkerson as an algorithm, but it could have been any other algorithm. Technical note: this should be any other algorithm that will find an integral flow if there is one. In this case, there is one. And then we return, and the subroutine tells us, hey, I found like a max flow. Now, this max flow is not the answer to our bipartite matching problem, right? What we wanted was a matching. So there was a procedure, some post-processing computation that said, okay, given the max flow, I'm going to read off or compute from it in some way a maximum matching. And so in this case, it was going to reading off which edges were selected by the flow. These steps of pre-process and post-process can be abstracted away as a reduction. So we're going to talk about now, give a definition of reduction between two problems, in this case between BM and MF. And so we're going to talk about it now. So let's remove these two claims. And now we're going to talk about reductions as a sort of, so formally. Reductions. So the first definition is that we're going to say that a problem A reduces to a problem B if any subroutine to solve B can be used to solve A. Well, this definition is not entirely precise at this point. Let me make it more precise. So, more detail. There exists two algorithms, efficient algorithms, we call them pre-process and post-process, such that, and I'm going to use pictures, otherwise because this English sentence is going to be too long. If you have some instance x for A, if you give this instance to the pre-process algorithm, it's going to produce an instance y for B. This is analogous to saying you give me an instance of a bipartite matching, and I pre-process it to construct an instance of max flow. And then, sort of, there is some way to solve B. This is any subroutine, so we don't care kind of what's inside here, just a subroutine to solve B. That will give us a solution, let's call it B of y. Actually, let me write it down here. And then given B of y, we provide as an input to post-process, and we get A of x, so the solution to the problem A. So the reduction itself is syntactically specified by these two algorithms, pre-process and post-process. Very importantly, the reduction does not say anything about whatever subroutine is solving B, okay? We don't care as long as it's solving B. In this sense, and also we use the notation for A reduces to B, A reduces to B. That's kind of the notation that typically gets used. Again, coming back to here, what has happened is we proved that BM reduces to max flow. How? Well, we didn't do it explicitly, we wrote two algorithms. The preprocessed algorithm gets a bipartite graph and produces a network. This network gets handed off to some subroutine for more solving max flow. At some point, it spits out, says, here's the max flow on this network you gave me. And then we implicitly thought about a post-process algorithm that will take this max flow and read out from it the matching. Okay? So in this respect, we reduced one problem to another. I'm going to say this again, that if A reduces to B, then we learn that if there exists an algorithm for B, then we have an algorithm for A. That's exactly what this picture says. It says, look, you give me an algorithm for B, me, the reduction, I know how to pre-process and post-process so that this entire thing is an algorithm for A. Okay? Conversely, we also learn that if there is no algorithm for A, then there is no algorithm for B. And this second part is very important. It will become very clear in the next lecture why the converse of this statement, the contrapositive of this statement is so insightful, because it lets us learn about hard problems, right? So if you think about, if you believe that there is no algorithm for A, and you're wondering whether B is also a hard problem, one way you can do it is you can say, well, look, I can use B to solve A. So in a very precise sense, A cannot be easier than B. And in this respect, if you really believe there is no algorithm for A, then you should also believe that there is no algorithm for B. Okay, so we're going to talk about this second part more next time. What I want to do for the rest of today's lecture is talk about a problem that is particularly strong, right? So you can think about reductions as basically connections between problems, right? But there are some problems that are more central than others in that many problems reduce to them. And if many problems reduce to them, it means that they're kind of, they're really more central, because solving those problems is at least as hard as solving any other problem. Or put it another way, solving those problems is tantamount to solving every other problem that reduces to it. And we'll show now that if this is the set of all efficient problems, one problem that can be used to solve any other efficiently solvable problem is linear programming. We're going to prove that linear programming, that everything can be reduced to linear programming. Okay? And this is a priori kind of maybe not clear, because linear programming is a sort of a priori just like some boring optimization problem. But it turns out that it has a very central kind of location in the map of problems, thanks to the language of reductions, because it can be used to solve any other problem as long as it is efficiently solvable to begin with. And this will be a warm-up to the type of discussions we'll have as we work our way up to intractability and the theory of NP completeness that will start next time. So my goal for the rest of the lecture is to just prove that all efficient problems reduce to linear programming. Okay, so I'm going to do it. Yeah, continue there. All right, so before we get there, there's a couple of definitions that we need to go through. The first one has to do with introducing the notion of the circuit value problem. first I need to tell you what is a circuit. So a Boolean circuit is a directed acyclic graph of gates of the following types. So you can either have an input gate that you can denote as either xi equals 0 or xi equals 1, depending upon whether that input gate has input 0 or input 1. One way you can think about it is that inside your graph you have like a vertex labeled 1, and you have the variable xi that points into some other vertex. You have also AND gates that specify that certain xi and xj should go to xk. Like in the direct acyclic graph, you can think about it as some gate that is labeled as AND, and it has the wire for xi coming in, the wire for xj coming in, and the wire xk coming out, right? So this is represented this way inside the direct acyclic graph. You can have OR gates, xi or xj goes to xk. And again, inside the direct acyclic graph, you can imagine there is some node somewhere labeled OR, and it has the wires for xi and xj coming in, and the output wire for xk coming out. You can have NOT gates. For example, xi NOT goes to xk, and so that is xi coming in, NOT gate, and xk coming out. And also, so one or more gates are designated as output. So this definition of Boolean circuit is precisely what you would expect. You just have like a collection of gates that are linked up in a directed acyclic, without cycles, by wires, and on the each vertex there are instructions on how to compute on the wires. So we're going to define the circuit value problem. Asks, given a Boolean circuit, is its output 1? Okay, so somebody hands you a graph. It is labeled with all these gates, and they're asking you, is the output 1? Now, the first thing to realize that this problem is efficiently solvable. Why? How? Because you can solve it as follows. You topologically sort it. You start from the sources, and you see what are the instructions, and you continue computing gate after gate. Look at the next gate. The next gate says, please take the AND of this other gate and this other gate, and you take their outputs, you AND them, and you label the output with the correct value. And you continue this way until you're done. And at some point, you look back, and you look at the output gate, and you see whether it is 1. If the answer is 1, then the answer to the circuit value problem is yes, and if it's not, the answer is no. Okay, so that's a pretty kind of sort of prosaic and mundane problem. But let me first maybe make some space here. A statement that may sound surprising. That I'm going to write claim. Let's call it claim 1. So every efficiently solvable problem reduces to the circuit value problem. Okay? So my claim is that if whatever problem you have, doesn't matter what it is, maybe we haven't even thought about that problem yet. If it is efficiently solvable, then there is a reduction to the circuit value problem. It seems like an odd statement to make, right? Because how could you talk about all efficient problems at the same time? Because we haven't even, like, maybe somebody hasn't come up with those problems yet. Like tomorrow, somebody else will think of a new problem, and it will turn out to be efficiently solvable. How can we already say that when that happens, then there is a reduction to the circuit value problem? Well, here, within this class, we don't really have the tools to prove this claim, so I will only kind of hand wave it and give you for the intuition. So what does we really mean when if a problem is efficiently solvable? We mean that there is an algorithm for it. But what is an algorithm? An algorithm is a sequence of instructions from a machine that say, I don't know, in some high-level language, there's some for loops, there is some if statements, there is some assignments, some computation happening. But this computation, at the end of the day, is like processed by the computer. And the computer, when you open it up, it's not like there's some magical box inside. There is circuitry. And at the end of the day, all of these instructions for the algorithm are translated to elementary digital logic. And at the bottom of it all, there's actually circuits computing. And if you unroll that computation, you take the computation and unroll it, you will find a Boolean circuit. Now, that's not a proof. It's just intuition. Now, the way to turn this into a proof, we would need the language of computability theory that you probably would learn if you take courses like 172. And where formally you talk about something like Turing machines. Turing machine is a mathematical model of computation. And the statement would look something like the following. If a problem is solvable in polynomial time on a Turing machine, then you can take that polynomial time Turing machine and turn it into a polynomial size circuit. Okay? So for now, the proof, I'll say kind of it is intuitive. And kind of the real proof is to take CS172 when it is offered. And this involves like kind of Turing machines and sort of having a mathematical understanding of computation models. So again, another way to view it is that every time you're solving a problem, you're implicitly finding a reduction to the circuit value problem. Okay, that is what is happening. The second claim that we're going to prove, like for real, is that we're going to prove that the circuit value problem reduces to linear programming. Okay? So this, we have the tools to prove because, we have a definition for the circuit value problem. We know what is linear programming. We have studied it. That's a problem. And we're going to prove we can write down a reduction from one to the other. And this will teach us that, in fact, everything that is efficiently solvable reduces to LP, which is potentially a surprising statement because linear programming doesn't, by itself, say anything about universal computation, about being as hard to solve as any other efficiently solvable problem. But this reduction places LP basically at the center of all efficiently solvable problems. So this is what we're going to prove now, that a circuit value problem reduces to LP. So let's make some statement, some space here. So let me rewrite the claim. Claim 2, which is circuit value problem reduces to linear programming. Poof. So we're writing a reduction. So let's first talk about the preprocess algorithm. In the preprocess algorithm, I'm given as input is a Boolean circuit. So I need to take, let me just maybe write first what we need to do. The preprocess, we need to take as input a Boolean circuit, C, and as output, we need to output a linear program, such that solving the linear program is tantamount to solving the Boolean circuit, or at least answering the circuit value problem about that circuit. Now, what is a circuit? It's a collection of gates, it's a DAG. And what is a linear program? Is a bunch of variables with linear constraints. So what we're going to do, first we can define the variables. So we're going to introduce a variable xj for every gate, xg for every gate g. So there is some number of gates in the Boolean circuit. For each such gate, we introduce a variable. Now, for the constraints, the first thing we're going to do is we're going to put a linear constraint on every gate and say that its variable is between 0 and 1. Okay, so that's a linear constraint. I can write it down. That's okay. And then we're going to put a bunch of gate constraints, one for each type of gate. So kind of for each gate, if it is an input gate, then we're going to write x g equals 0 or xg equal 1 as needed, depending upon what was the gate doing in the original circuit. Either of these things is a linear constraint. For the AND gate, so for the AND gate, it's not super clear, right? Because we have this AND computation, which doesn't look like a linear constraint. Actually, here I want to call the gate I. Or no, K. I'm going to call it K. Right. So an AND gate involves a computation that doesn't a priori look like it's linear. But here we actually can use a trick where we have a collection of linear constraints that simulate an AND computation. So I'm going to write it down first, and then we can reason about it. We're going to write xk is at most xi. And here in AND gate, I mean that we're looking at xi and xj goes to xk. If whenever that's the case, here we write the constraint xk is at most xi, xk is at most xj, and xk is at least xi plus xj minus 1. So let's kind of check that these linear inequalities are actually computing in the AND gate. Let's say that we have 0 and 0 as input. We would expect the output to be 0. Okay, so 0 is at most 0. That's fine. 0 is at most 0. That's also fine. And here it says 0 is at least 0 plus 0 minus 1, right? So this is saying that 0 has to be at least minus 1, and 0 should be at most 0. It is the only 0 is the only value for xk to satisfy these constraints, so we're computing correctly. Let's try more case analysis. Say that we have 0 and 1. The output should still be 0. Well, here it says that xk should be at least 0, so at most 0. Xk should be at most 1, and it should be at least 0. Again, xk being equal to 0 is the only possible answer. If we have, let's say, 1, 0 is by symmetry, so let's try 1, 1. 1, 1, the output should be 1. Okay, so xk is at most 1, xk is at most 1, and here it says xk should be at least 1 plus 1 minus 1, which is 1. So again, the xk being equal to 1 is the only output. I mean, it's the only reasonable possible assignment to xk. So for the OR gate, there is a similar but kind of symmetric constraint. Xk is at least xi, xk is at least xj, and xk is at most xi plus xj. I will not do the case analysis again, but it's sort of similar. And for the NOT gate, we have that xi minus 1, sorry, 1 minus xi is xk. Okay? So all of these are implementing each gate as a one or more linear constraints. And in fact, it doesn't even matter what is the objective function. We have defined variables and constraints, and the way that these work is that in the polygon, or rather in the polytope, that of feasible solutions, there is only a single feasible answer, which is the correct answer of the values of the Boolean circuit. So for the post process, the answer to this problem will be some x star, which is the optimum, the only feasible solution to this linear program. And if we want to answer the question of the circuit value problem, the way we post-process this answer is that we just pull out whichever is the output, and we see whether it equals to 1 or not. Okay, so post-processing just means look at the answer that the LP solver gives me. This is the only feasible solution anyways. This is basically the wire values of all the circuit. And if we want to answer the original circuit value problem, the way in the post-process we do it, it will say, okay, what was the output gate? It's this one. We go and see it. And if it is 1, the output to the circuit value problem is 1. If it is 0, the answer is 0. So this shows that we can kind of program, linear programming, an LP instance to do general purpose computation for us. Because this is like a circuit, like an arbitrary Boolean circuit, and the LP solver will be compelled to do this computation for us, because that's what the linear constraints say. Now, because LP, so I want to make a point here. So we just went through an example where A is the circuit value problem, B is LP, and we wrote a pre-process and post-process algorithms. Now, crucially, pre-process and post-process need to be efficient algorithms. Now, there's a bit of a technicality here that when both A and B are efficient, you could have kind of like a stupid reduction where the pre-process algorithm solves the problem but doesn't tell the reduction. So you always want the pre-process and post-process to be kind of weaker than the resources needed to solve the problem B, so that you're actually reducing as opposed to like fake reducing. Whenever you're reducing between efficient problems, it's not enough to say that the pre-process and post-process are merely efficient. Typically, what you will find in a computability course is that you also want to run them in so-called logarithmic space. So they're even weaker than just efficient. They're logarithmic space polynomial time algorithms. And if you go through this reduction here, this kind of producing linear constraints for each gate is actually a small space algorithm, okay? In that space, we could never have hoped to accidentally solve the original circuit value problem. Within logarithmic space, we really are quite limited. We have our hands tied, and reduction really is like is working less than the subroutine for the linear program. This would be like a technicality that is not very important starting from the next lecture, because we'll be trying to kind of relate problems for which we don't have efficient algorithms. So having pre-process and post-process being merely polynomial time algorithms is kind of good enough. So, all right, coming back to here, the way to think about reductions is they're a lens or like some tool to merely relate problems. Again, when you're like thinking about writing a reduction, you're not solving either problem. You're not providing an algorithm for A or an algorithm for B. It's saying that if you have an algorithm, in this case for B, then you have an algorithm for A. This is just a thought experiment. Okay? Maybe you will never come across an algorithm for B. What instead you are being asked to do is to relate the problems. relating the problems consists of writing down the two algorithms, pre-process and post-process, that are preparing the instance and solving the instance. Okay? And so reading and translating the answer produced by the subproblem, by the subroutine for B. So today, to recap, we saw as a motivating example how to reduce bipartite matching to a quite different problem, max flow. We saw another reduction from the circuit value problem to LP. LP, at this point, we know that is as hard as all efficient problems. And starting from next time, we're going to leave behind problems that we know that are efficiently solvable, and start studying problems that we do not know are efficiently solvable, and in fact, we do not believe that they are. Yet, reductions are going to continue being like a kind of a flashlight that lets us understand kind of relations between problems without ever having an efficient algorithm for any one of them.